With that, let's see. This is, I don't know how many times I'm going to let them know, hey, you need to update your username. This is going to start affecting things. Let me share my screen.
Professor C?
Yes.
When I get back to my dorm, I'm going to join off my computer. So I'm going to just say, like, my computer is in the waiting room.
Okay, it's fine. That's fine. I just added a student. I don't, it says Zoom user, so I don't know who you are. I don't even see you. Where are you? Like, did you get booted or something? Okay, now I think you changed it to Marcus. What's your? Let's see.
Yeah, that's me, Marcus Henderson.
Henderson. Okay. Yeah, because I let you in. Just if you could have that up there before you get into the waiting room, that way I can just give you credit and keep it moving.
No, because definitely, I got you.
Yes, no worries. Let me see. Let me go ahead and share my screen. Start the broadcast, and we can do some updates. Matter of fact, let me do this real quick. Go to my settings, and I'll just do this for a little bit until it gets distracting for me. Then I'll disable it. Okay, let's start here, and let me kind of do some quick updates. Let me back up, and I actually like to start here. Okay, let me go to view, a single page. Okay, we'll start here. Let me see. So as far as announcements, I hope everyone had a great weekend. I think this is the week before spring break. So I think the structure of our course, right, we're doing 2 exams, right? So we already did exam 1. And my goal was to have your grades ready by today. They're just not ready. So you got to give me until Wednesday. And it's just that I have my class that's right after you all. They're on essentially a quarter system, but today is their last day. So I was trying to prioritize theirs and, so with prioritizing theirs, I didn't get to you all's, but also because we have until Wednesday. So I should have the grades updated by Wednesday. And it should include pretty much the grades through chapters 1 and 2, whatever is due up until that point, but I usually, at least through chapters 1 and 2. Trying to think if there's anything else. Are there any questions for me before we kind of get into it? Going once, going twice. Let me see. And I think we have spring break next week. I wouldn't be mad at you if you started traveling early, but at a minimum, if you at least just try to log in, if as long as you're logged in, get your credit, then I usually don't press too much about. I think I got
real quick before you start the lesson. I'm in the way. Never mind, you got it. Thank you.
Yeah, that was the technique that I was trying. That was different. Was usually I have my notifications off when you guys are coming and going in the waiting room because it's distracting for me. But I was like, well, let me just turn it on for a little bit. And I know that was you, so it's like, okay, so that's not too bad. And that actually helped a lot. Let me see. Yeah, so I do intend to have your grades ready by Wednesday, so that way you can have some feedback. You can make a plan going forward. And I know last time I think we did 3-3 and we didn't get a chance to get through 3-4. And I was like, hey, I want you to use my recording. Oh, this is a long section too. I was hoping it was going to be short. I do want to take some time today to kind of touch on 3.4. I might do a few examples. We're really supposed to be on 3.5 today. So we can't really get through both of them. So I am still going to have to rely on my recordings. But I do want to take some time to just look at 3.4 optimization, finding absolute value, max and min values. Actually, I don't want to be like it's a repeat of the previous, but it's heavily using the previous. So maybe I might just leave it in my recording. Let's use the recording. Max, let me see, max and min principle 1. Let's look at it. Suppose f is a function with a domain I. We say f of c is an absolute min if f of c is less than or equal to all f of x and a y. So it's an absolute minimum if it's the lowest y value. So when it comes to finding absolute max and min, the procedure is pretty much the same as how we find the local max and min, but then we just also have to test endpoints. So whenever we're talking about absolute max or min, it should be on a closed interval, meaning we include our endpoints. And so now we just do our test like we did before with the first derivative test, second derivative test, stuff like that. But then we also test our endpoints, all right? So it's a repeat of the previous section, and you also test the endpoints to find the maximum. We can do at least one example. I think I accidentally double-clicked there. Okay. So the extreme value theorem, a continuous function f defined over a closed interval, meaning we contain our endpoints, A and B, must have an absolute maximum value and an absolute minimum value over that closed interval. Suppose that f is a continuous function defined over a closed interval AB. To find the absolute maximum, first find the derivative, determine all your critical values on that closed interval. And those are going to be the values where the derivative is either 0 or does not exist. List the values from step B and the endpoints, and then whichever one of those values has the highest y value is your max. Whichever has the lowest y value is your absolute min. Right. So again, the procedure is the same thing as we did in section 3.3, where we were doing first derivative test, second derivative test. The only difference is now we have some endpoints that we need to test as well to get the absolute max and min, right? I'll do this one because I think it's quick. It's a first glance. Let's grab this. So this one says, let me see, we want to find the absolute maximum values of this function over the interval from -2 to 3/2, right? So we want to find all like extrema, right? The critical values. The relative max and relative min are going to occur when the derivative is either 0 or undefined. Give me just a moment. Matter of fact, I think I had a technique last time. Did something like this. Mr. Ford, let me get him. Here, got him, coach. All right. So last time, we take our first derivative, and then we can either use the first derivative test or second derivative test, to identify our max or our mins, relative max or mins, right? So let's take a look at the derivative. Hopefully, by now you've already taken the derivative of this guy. So if we're looking at f prime, the derivative 3x squared minus 3, okay? So then the critical values are going to occur when either the derivative is either 0 or it does not exist, right? So if we set this guy equal to 0 and solve, if we factor out 3, we'll get something like x squared minus 1 equals 0. So then x equals plus or minus 1, right? So when x is either 1 or -1, it makes the derivative 0, right? So then I think on the previous slide, it was saying that once we have our critical values, yeah, then we list out our critical values along with the endpoints, and then whichever value has the highest y value is our absolute max, whichever has the lowest y value is our absolute min, right? So we'll do something like, we can say x versus f of x. So our endpoints, we have -2, let me see, -1, 1, and then 3/2, right? Okay. Let me go ahead and get my calculator ready. How do I want to do it? This is fine. I know I got multiple things there. Let me get rid of all this stuff. Let's go here. Oh, somebody is cooking and it smells good. All right. Okay. And okay, +2. Okay. I'm going to go to my y equals. We got x to the power of 3 minus 3x plus 2. Okay. And I just want to test this function at these x values. So I'm just going to go, I'm going to call on that function. If anybody needs to know what buttons I click just there, just let me know. I know I've explained it several times, so that's the only reason I went fast. So when we plug -2, let me make sure I got my y equals proper. When we plug in -2, we get a corresponding y of 0. Let's plug in -1. We get 4. Let's plug in +1. We get 0. And when we plug in 1.5, or let's just do 3/2, just 3 over 2. 3 over 2. Let's hit math as a. I'll get them in just a moment. So 7/8. Okay. So it looks like But this is our absolute max here. And it looks like the min we have, it occurs in two places. I know I can't pull that because I got this open. Oh, we got a whole slew of people. What is going on? Let me see. Main lemons and Odin. Main lemons and Odin. So many interesting names. I always think like, are you guys related to celebrities or are you celebrities? Got another one. So get to student. All right. So it's like, I don't mind having the little notifications on like this as long as people are coming, but once I start hearing people leaving, it gets distracted and it kind of irritates me. So that's when I turn that notification off. So as long as I don't hear people leave, you know, then I'll leave it on and I can get people when they arrive. Okay. So find the absolute maximum and minimum values over this interval. So we took the first derivative, we set it, we found the critical values. So when the first derivative is either 0 or undefined, and we compare those with the endpoints. And these are the results that we got. Okay, let's see, how do we do? Plus or minus 1. So those are our x values, the corresponding y's. I think we got the same thing. So the maximum value on this closed interval is 4, which occurs when x is 1, and the absolute minimum value of 0 occurs when x is 2 and 1. Wait a minute. Wait, something's not right. Back up. Let's go here. With negative 1, what are the 4 should be, that should be negative 1 here. And I think that's what we got though when we did it. Yeah, all right. So hopefully that made sense, right? So again, section 3.4 is really an extension or a continuation of 3.5. And that's the main gist of absolute max and min. It's the same as 3.4. It's just, in addition to those relative max and mins, we also test our endpoints, right? Let me just do a quick scan. Quick check I usually leave as an exercise for you. Let me see, suppose that if it's a function that exists for every x in an interval, and there is exactly one critical value, then that critical value is either an absolute max or an absolute min. Let me think. Okay. So what this max min principle 2 is saying that when you go to find your critical value, if you only have one critical value on a closed interval, then that critical value is going to be either your absolute max or your absolute min, right? Because that's either going to be the top of a mountain or the bottom of a valley, right? So it should be one max or another. I'm gonna leave this one as an exercise. So I mean, that's the main crux that I wanted to kind of pull from this one. And if you want for more details or further details on this, I'm going to have to rely on my recording. This is just what we were supposed to do on Thursday. We didn't get a chance to. We ran out of time. And I think I made a copy of this already available. It's blank, but you know, you have it there along with the recording. So if you want those details, it's there. So our official start for today is here. It wasn't too bad. We actually did much better than I thought we were going to do. Is section 3.5. So the goal for this week, so now the rhythm kind of changes a little bit. I know for a good while we were doing 2 sections a day, which I will admit is a little bit intense, but you know, we have to do what we have to do. So really, our goal for today is just 3.5. So if we finish it, then maybe we can like work on some questions together. So let's see what we're looking like. Yeah, I'm assuming you guys and everything is okay. We're pretty good about if it's not. Okay, so we're continuing chapter 3 on applications of differentiation. And we're working on section 3.5, optimization with business, economic, and general applications. The objective here is to solve optimization with your max and min problems using calculus. Okay, so let's see if we can do this. A strategy for solving maximum minimum problems, read the problem carefully. If relevant, make a drawing. Number 2, make a list of appropriate variables and constants, noting what varies, what stays fixed, and what units are used. Oh, I remember this can be kind of dicey. So we're gonna do the best we can. Label the measurements on your drawing if one exists, okay? Translate the problem to an equation involving the quantity Q to be maximized or minimized. Try to represent Q in terms of the variable in step 2. And in step 4, try to express Q as a function of one variable. Use the procedures developed in sections 2.1 to 2.3 to determine the max or min values and the points at which they occur. Done. No. Okay. All right, let's give this one a go. So from a thin piece of cardboard, 8 inches by 8 inches, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume, and then what is the maximum volume? I like this one. I like this one a lot. Okay. So we're working with cardboard, right? Do I still have that color? I do. Okay. So we're working with a piece of cardboard, and it sounds like it's a square if it's 8 inches by 8 inches. I'm actually going to do this and readjust it, all right, to just look more like a square, okay? And let me see, we're cutting out square corners so that the sides can be folded up, right? So let me do something like this. Yep, that's exactly what I want. We're going to copy and paste. Actually, let's go style. Okay, that's good. Let's copy and paste. All right, so we're cutting out these square corners from my piece of cardboard. Now, paste. Okay. So then we're going to fold it up, right? So if we're going to fold it up, we're going to get something sort of like the following. Okay. Oh, no, that's not what I want. Let's delete that. Let's actually just copy this and paste. And I'm going to readjust, sort of like that. Let's go style and dash line. Nope, try that again. Style, dash line, right? So this is the idea, right? Let me see. A thin piece of cardboard, 8 inches by 8 inches. So it's saying that this is 8 inches and this is 8 inches, right? So this, as this goes from here to here, is 8 inches. And as we go from here to here, are 8 inches, okay? Just being a little bit OCD. That's a little bit better. Okay. And we're cutting off square corners. What dimensions will yield a box that will maximize the volume? Let me see. So it seems like the thing that we can change is like this distance from here to here, right? There's my Q. Give me just a moment. Settings, because that's going to distract me. But I got a few people as they came into this. I'm happy about that. Okay. Right. So we can change or vary the size of that square, right, that we're cutting out. So we want to see like, okay, we want to what? Maximize the volume. I think these are pretty much most things that are at play here, right? And so then like when we cut out the square corners, let me see. We're going to get something like the following, right? Let's copy and paste. We're going to fold up our flaps in just a moment. So something, I guess, you can go like about there, I guess. And then let's go like this. Oh, that's new. Let's copy and paste. Uh-oh. Okay, so we need to adjust this one as well. Okay, this looks decent. And let's do it like this. I'm just being whatever. Let me kind of go like that. Let me think. About like that. About like that. I think that'll do it. So then if we highlight, let me see. Yeah, undo. Let's go style. We want it to be dashed because it's like behind the scene. Style, dashed. Oh, we missed one. Do do how do I capture that? Okay. Sorry. Yeah, I don't understand. Oh, maybe it's because they're overlaying each other. I see what's going on. Okay. So let's do it like this. Partial. We're gonna cut it about there. Then we can do the whole. We can get rid of that one and then put this one back. And that works. Okay, that's essentially what I wanted. All right. So hopefully this setup makes sense, right? We're starting with an 8x8 cardboard box. We're cutting out those square corners, and we're gonna finish with an image like this, right? So then if we translate, right, the height of this box, this is gonna be our X from our original drawing. And then like, let me see. If that's X, then what? From like here to here, this distance is going to be what? 8 minus 2x? Because the whole thing is 8, and we're removing, if we just want that edge, the edge is going to be 8 minus 2x, right? From there to there. So over here, that would translate, this is going to be 8 minus 2x from here to here. And I think here also is going to be 8 minus 2x from here to here. Okay. I think this is okay. All right. So we can, we can let this be our height. This can be our width, and this can be our length. Okay. Okay. So then we want to maximize the volume. So then what? Volume of the final product should be what? The length times the width times the height. So it looks like we can write the volume in terms of X. So then it looks like it's going to be what? 8 minus 2x times 8 minus 2x times x, right? So now we have the volume in terms of the height. Let me get some space. I think what I'll do, I'll duplicate this. And I'll just I'll clear this one. Clear, hang on. Oh, there we go. Clear. Okay. Okay. All right. So again, let me kind of start here. So we have the volume in terms of x looks like it's 8 minus 2x times 8 minus 2x times x, all right? So we want to maximize this guy. Okay, so let's expand this out, all right? If we FOIL, let me see, what is that, 64. Let me see, 2 times, or 8 times 4 is 32. Outer, let me see, outer, inner, yeah. 2 times this, so negative 32. And then plus 4x squared, and then we need to distribute an x into that. So then the volume in terms of x, when expanded, we're going to have like 4x cubed minus 32x squared plus 64x. Okay, so then if we want to maximize this, let's look at the first derivative of this guy, all right? So v prime, that's going to be what, 12x squared minus 64x plus 64, okay? So then if we set this to 0, let me get rid of this. Looks like we can factor out, oh, we almost can factor out a 12. 6 and 4 is what, 10? Maybe we can factor out 4. If we factor out 4 from everything, we have what, 3x squared, 124 is 6x. Okay, I think that's about the best we can do there. So then what? AC method of factoring. We're looking for two numbers. what is that? 30 and 18 is 48. Two numbers that multiply to give us 48. Okay, and add to give us 16. Now 48 is what? Is that 6 and 8? 6, 42, 48. So then that's 2 times 2 times 2 times 2 times 3, right? So I'm gonna do all my combinations of the factors of 48 and stop at the line that adds up to 16. Okay, so for instance, 1 and 48, but that doesn't add up to 16, right? Now if we do 2, if we've used this 2, what's left over? 8 times 3 is 24, right? So those add up to 26. So these are not the 2. Okay. We can do 3 and something, right? So if we've used this 3, what do we have left over? 16? We're almost there, actually. But these are not the 2 numbers. Can we do 4? Yeah, we can do 4. Right? If we've used 4, what's left over? 12. Okay. And I think those 2 numbers added to 16, but we want negative 16, so then we'll do negative 4 and negative 12. I think these are the 2 numbers that we're looking for. Okay, so I'm just factoring, right? So now you could do factor by grouping at this point. I'm going to use this box method. In the upper left, I'm going to put this 3x squared. Bottom right is a 16. And that negative 16x, I'm going to rewrite using the 2 numbers I just found. Okay. So then we can do something like negative 4x and negative 12x, right? So then when we go to factor this guy, if we look at the 2 on the top of the box, what do they have in common? Looks like we can factor out x from both of those guys. The 2 on the bottom looks like maybe a negative 4. So we can factor out a negative 4 from those guys. Okay. The 2 on the left, it looks like we could factor out a 3x. Okay. And the 2 on the right, it looks like is also a negative 4. Okay. I need more space. But our claim is that now this guy now factors. We got what? 3x minus 4 and x minus 4. Let's do a quick FOIL to make sure it works. 3x squared, that's going to be minus 12 minus 4 is minus 16, and negative 4 squared is positive 16, right? So then from here, our critical values, what do we have? 4/3 and 4. All right, so those values of x make the derivative 0. Let me see. Inches, 4 inches. Okay. So then we have, we need to test, the same way we did in that earlier example where we have our endpoints, right? The smallest value that x could be is what, 0, and the largest value that x could be would be 8. So we could make a table. I guess I'll use this space. Let me I'm gonna shrink this down and just kind of work on the side of this guy. Let's keep this here for like reference. Okay. So then, like we did in the early example today, we have our x versus our volume, right? Again, the smallest x could be would be 0, which more than likely it's not going to be there. So we got critical values of 4/3 and 4. And then the largest the x could be also, which more than likely is not the answer, would be 8. Right? Because it's like you're not cutting out 0 and 8. It's like you're not cutting out an x at all. So then we're going to say, okay, which one of these values creates the largest volume? And then we're going to say that's our max, right? Okay, I don't think I have it ready, so I got to go like this. And our volume function is, we'll use that one. Okay. So we'll go to our y equals and clear. We got this 4x to the power of 3 minus 32x squared. Okay, plus 64x. Okay. So then I just want to call on that function. I want to evaluate this function. Let's just see what happens when we plug in 0, just for the sake of doing it. That makes sense, right? Whatever. Yeah, because we don't have any flaps to fold up. So I would anticipate this being 0, this being 0. Let's check 4/3. And let's hit math as a fraction. Let's remove the fraction. So that volume square inches, so about 37.9 square inches. Okay. And what about when x is 4? Okay. Well, if we did this properly, right, based on our results, so we got that 4/3 and 4 were critical values. So it looks like the volume might be maximized if we cut out 1 1/3. If we make the squares 1 1/3 inches. So then, if the square is 1 1/3 inches, length, width, and height. Let me see. We get that the height is 4/3 inches. So then 8 minus 2x. Let me see. 8 minus 8/3. 24. 24 minus 8. 16/3. So we got that. This should be 16/3 inches. 16/3. This is the result that we got. I'm just trying to think, did we make a mistake somewhere? Or how does this sound feasible or realistic? That's irking me. Delete. Okay, let's see how do we do. Right? Now, copy. Let me see something. If I go here, and let's kind of test those. Wait a minute. Okay, so we got a maximum value of 37.9, so about 38 square inches with these dimensions. Let's see if these dimensions give us that volume. So if we say like 16/3 times 6, or we could just say squared, I guess, times 4/3, do we get the 37? Yeah, all right. Okay. So let's kind of compare it to, that's about the best we can do, you know? Between the previous slide and this one, I think that captures everything. All right, so we have a drawing, right? They started with a square, 8x8 cardboard sheet. The height of those squares, or the squares of the variable x. Then we fold it up, we got our 8 minus 2x where the height was x. So I think we got everything the same here. I think we got all of this. 0 to 4. X must be, okay, yeah, because I guess once you go beyond 4, then it's like feeding back on itself, right? So we put an 8 where we should have put a 4, but this is fine. Still, the idea is still driven home. All right. And then, so 4/3 is the only critical value from 0 to 4, right? So we tested before, we saw that it didn't work. Now, they use a second derivative test, right? If we want a maximum, that means it should be negative in the second derivative. And it is. You can see it here. You get a negative result in the second derivative. So that means that with that value being negative in the second derivative, that means the original function is going to be concave down, which means we're going to have a maximum value, right? And I think that's exactly what we got. So the volume is maximized when 4 1/3 inches are cut away from each corner, and the maximum volume is the same thing that we got. Okay. That was fun. So I think we got that one all the way. Okay. Leave this as an exercise. Okay, let's get this one done. I feel like this one, sometimes these, like, there's something that I'm usually missing for some of these, and like they give me a hard time. I like the last one. I don't know, like when it's, construction and visual and shapes, I resonate with that a little bit more. But let's give it a go. So in example 2, a stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be this. Okay. The manufacturer also determines that the total cost of producing X units is given by this. Let me see. To sell X units, the price per unit must be this, and then the cost is this. Find the revenue, so the money generated. The money generated is going to be the price you sell, the price of each item times the number of items sold, right? So we have a function for the price. So the revenue would be the price, or P times X, right? The price times X, okay? Profit is going to be revenue minus cost. So once we have our revenue function, the profit function is going to be our revenue function minus our cost function. So that's not too bad. Let's go ahead and do those actually. So the money generated, our revenue, and I'm going to use a different color. Let's do, I guess, purple, just to make it pop a little bit. So this is going to be the price we sell each item times the number of items sold. Okay. So then we can just jump straight to here. Negative X squared plus 1000X, right? I just said X times the price function. Let me get something like this. So that's our revenue function. Okay. Let me highlight it. Okay. So then the profit function, that's going to be the revenue minus the cost, or the revenue function minus the cost function. Okay. So we would say the previous answer minus the cost. Okay. So then we would have something like this. Negative X squared minus 2X. Shoot. Okay. So 1000 minus 2 was what? 998. Okay, we subtracted 2X and we subtract 3000. Okay, so that should be our profit function. All we did was the revenue function that we generated minus the cost function. When we said minus the cost, we had to distribute that negative and we got this result. Okay, so we got our profit function. Let me highlight this guy. How many units must the company produce and sell in order to maximize the profit? So we want to maximize this profit function. So we probably need some space. And we probably look at the first derivative of the profit function. And then, like we did in the previous few examples. All right, so I guess I have to go, this is slide 16. We're about halfway. What's the time? Let me get a copy of this. Drop it on 16 right here, paste. Okay. And this is our profit function. I'm gonna get a copy of this guy. Oh, also copy. If you're just in town and you wanted something to do this weekend, at the High Museum of Art, I want to say the second Sunday of every month is free admission at the High Museum. I think it runs from, it might be like noon to 4. You can gain free access. If you just, I don't know if you've ever been to an art museum. It can be kind of weird and boring, but it's just something to do that's free, right? So the second Sunday of every month is free admission at the High Museum. So yeah, it's always, and they do a pretty good job of like at least having at least one new exhibit at each month, right? So you'll see a lot of similar ones if you go repeatedly, but you should be able to find at least one new exhibit, like a whole like wing or something devoted to like one new exhibit. So it's just something fun to do. Okay, so let's maximize this profit function. I feel like that was a word from our sponsors, and they are not our sponsors. It's just when I be watching these YouTube videos, they always kind of have some way to get a sponsor in there. And that's kind of what that felt like. Free advertising or free marketing from them. So it's just something fun. All right, so say this is our profit function. And we want to maximize this guy. So let's look at P prime. And I'm going to switch. I think I'm going to go ahead and switch back to black. So P prime of X, negative 2X plus 998. Okay. So this is the critical value is going to occur when this is either 0 or undefined. So if we set this to 0 and solve, subtract and divide, X equals, what is that? 4, 9, $4.99. That makes sense, right? So the critical value we got was this. Now in the previous example, they looked at the second derivative. So we can do that. That shouldn't, since we only have one critical value, all right? So if we look at the second derivative, looks like we get a -2. So no matter what x value you get, the second derivative is always negative, which means the original function is concave down. So this implies that this is a maximum value or absolute maximum value, right? Because the second derivative is always negative, that means the original function is concave down. That should be a max. So it looks like we need to produce and sell 499 of our units in order to maximize the profit. That's what it's looking like. And then we plug this value into the original to find out what's the maximum profit. Put it here. So we got a negative x squared plus 998x minus 3,000. Okay. And we want to evaluate this function when x is 499. So our claim is that the maximum profit is $246 and $246,001. Okay. So then the max profit when x is 499, 246,001. How many? Okay. So we found the total profit. How many units must the company produce and sell in order to maximize the profit? We got that x was 499. That's what we got. What is the max profit? So we got the max, can't write today. The max profit at the sale of 499 units was that 246,001. What price per unit must be charged in order to make this? What price per unit must be charged in order to make this maximum profit? Okay, so price per unit. Okay, so right here, let's do this. We got the price per unit. We got 1,000 minus x. So we got P of x equals 1,000 minus x. And we got a max profit of this 246. So then the 246, if we're selling the items at P times 499 units, right? What do you think? So we would have this 1,000 minus x, that's the price per unit, times 499 units to give us $246,001 right here. So now we have one equation, one unknown, so we should be able to solve. Okay. I think I'm gonna keep working over here. If we distribute the 499, okay. So we get the 499,000 minus 499x equals the 246,001. So we get a negative 499x equals, just do that subtraction. So we can say that minus 499,000. And we get this negative 252,999, right? So then we say that divided by a negative 499. So $507.01 is approximately So we need to sell each unit for at least that amount. Maybe just raise it to like, maybe take the ceiling. So maybe say 2 cents. Anything above that, actually, it might go into the law of diminishing returns, because like if you go too high, I mean, I'm pretty sure it's not that exact, but you know, if you go too far, if you sell it for too high above this, then people won't want to pay for it, right? So based on this data, right? So we got 507 and 1. Not X, but the price. Okay. I feel like this is okay. Let's see, how do we do? So for A, so our revenue, did we get that? Yeah, X times P. Yeah, I think we got that. Oh, 80. Looks like we made a mistake. 20. Wait a minute. I think there's a typo somewhere. Cost function. Let's look at our cost function. I think that's where the mistake is. I knew something was looking weird. I see, yeah. I think that's supposed to be a 20 and it's a 2. So if we want to match what the textbook has, we would have to go back and redo everything with that being a 20 right here. I think this is supposed to be a 20. So let me just cross this. It looks like it's supposed to be a 20x. I mean, it wasn't that difficult what we were doing. I just don't want to do it, but I do want to see if we did it right. So I'm just going to bite the bullet and redo it. Okay. So if we say that minus this, so minus 20. So instead of that being 998, I'll do the changes in green. All right. When we go to subtract, we're going to subtract 20x. So 990, 980, right? That's going to be 980x there. That stays the same. Okay. So let's get it. Yeah, let's just redo it, because I'm curious, right? And I know that sucks as far as our time, but that happens sometimes, right? So we got a new function. Let's just duplicate this. Come on. We're going to clear this guy. Damn, I need to go and change my notes so that I don't make that mistake going forward. Nope. Delete. Let's try this one more time. Copy. Paste. And this is our profit function. I'm just trying to go a little bit quick. I see the time. We still got to solve like 20 minutes. So then P prime, negative 2x plus 980. If we set this equal to 0, subtract and divide, x equals, let me see, that's 4, 18 is 9, 490. Okay, that makes sense. Units. All right, let's look at the second derivative real quick. We still got our negative 2, so this should be a max value. All right. Same argument as before. Okay, so that changes right here. Instead of 499, we got what, 490 here? $490 units. And then, so we plug the 490 into our profit function. Do we still have that saved? We go to y equals, that needs to be plus 980. Okay. And then 2, 3. That needs to be 490. Okay. So that's 490. Okay. Now we're getting 237, 100. So we're saying that's the max profit when we produce and sell 490 units. And then if we do a similar thing like we did for the last part, it wasn't too, it didn't take up that much more time to redo that stuff. Right. Okay. So the 1,000 minus x times 490 is this guy that we gotta fix, right? So if we say the 1,000 minus x times the 490 to give us the 237,100. Okay. Let me see. 490 with 3 zeros. 490x. 237,100. 490x. So we're going to say that minus 490, 1, 2, 3. We should get a negative 252,900. We're going to say divided by 490, divided by negative 490. Okay. 516 and 12 cents. So then 516 and 12 cents. Let's see, how do we do? Okay. All right. So now after that adjustment, let's see, how do we do? So now we got that. I think we fixed the cost function. It was supposed to say 20. I need to go and update my notes with that. We got the 498, 980, I mean, 490 looks good, negative. So it's the maximum value. 237,100. I think we got the 510. Wait a minute. There's some rounding there. 490. Oh, they just plugged the X in. Okay, so I think we just got that part wrong. It wasn't that far off. I don't know why it's so different. Maybe because of rounding. But yeah, they just put the X in, which makes more sense. Okay. All right, so for that last part, we should have just plugged in. Just want to update my notes. Let me think. Okay, I'm gonna strike through this, and we should have just said P of 490, and then you get your result there. 1,000. This is gonna be 1,000 minus 490, so 510. I'm trying to think why is that so different than what we got, but that's okay. Okay, that wasn't too terribly bad. Okay, let's try to keep going. Since we'll say for like no more than about 10 minutes. Or if we finish this, we might finish this. So we got a quick check. I'll leave as an exercise for you. Let's take at least 10. We'll take 10 minutes on this. I don't know if we're going to finish it or not, depending on. It just depends. So we have life sciences, concentration of a drug in the bloodstream. A drug is administered into the bloodstream of a patient. Let this represent the concentration in nanograms per milliliters of the drug in 10 minutes after it's administered. What is the peak concentration of the drug in the bloodstream, and when does this peak occur? Right, so we basically want to maximize this function. So we need to look at the first derivative. Right, so let's start there. So let's start with C prime of T. Looks like we got to use the product rule, right? We got the T times the E. So the product rule is what the first. So I'm gonna designate this as my first guy. So the first times the derivative of the second. The derivative of E is itself times the derivative of the power, which is negative 0.04. So that's the first times the derivative of the second plus the second, which is this guy, times the derivative of the first, which is just 25. Okay. Idealistically, let me see. We want to set this to 0 and solve, and our critical value is going to occur when this guy is either 0 or undefined. Now, let me see if I can rearrange some stuff. looks like we can factor out an E and a 25. So if we factor out 25e to the negative 0.04t, okay? Now what are we left with? On the left-hand side, the e is gone, the 25 is gone. It looks like we're left with 0.04t. On the right-hand side, it looks like we're left with a 1, okay? So now, and we want to set this to 0 and solve. Now, this guy on the left, will this ever be 0? Right? This is exponential decay, and it's above the x-axis. So I don't think this guy will ever be 0. We can't find a t to make this 0, right? So then I think that our 0 is only going to come from this guy. So if we set that to 0 and solve, subtract, it's going to be what, t equals 1 over 0.04. So what is that, 25? Because that's like 4 over 100. So 100 divided by 4 gives you 25. It's the time in seconds. What are the units for t? Minutes, 25 minutes. I guess that would be a pretty strong 25 seconds later. You know, it's peak concentration. I don't know. I imagine I'm tweaking or peaking or something. Anyway. Okay, let me see. Now we could look at the second derivative. I think that's just going to be a bit extra. We could also like do test points on either side of this to confirm that it's a maximum. It should go from like increasing to decreasing. T minus, what's the peak concentration, and when does this peak occur? Okay, so what we should do, we do want to confirm that this is indeed a maximum. So like if we choose a t value on the left to test in the first derivative and a t value on the right, the result should go from increasing from positive to negative to show that it's going from increasing to decreasing. Or we could look at the second derivative, which I don't think I feel like doing because it just looks like a bunch of extra for like no reason. Maybe. I mean, we could do it. I'm just being a little bit lazy. But we can still just use the first derivative test, right? Let me kind of glance at it. If you did like 24, that's going to be a positive result. 400s. 24. 80 plus 16 is 96 over 100. I think it's less than 1, so that's positive, right? So if we plug in 24 into the first derivative, it looks like we get a positive result. If we plug in 26, I think that's going to be positive, and I think that's going to be negative, right? So yeah, if you choose a number left of 25, you plug it into the first derivative, you should get a positive result. You choose a number to the right of 25, you plug it into the first derivative, you get a negative result. So that implies that the original function is going from increasing to decreasing, which means that 25 should be a max, a maximum value. Okay. And what is the peak concentration? So we would just plug this into our concentration formula that was given. So I'll just do it here. We could just do 25 times E to the power of negative 0.04 times 25. Okay. Peak concentration, nanograms per milliliter, 229.92 approximately. And this is what, C of. So our claim is that after 25 minutes, the concentration is going to be maximized. Hopefully that made sense, right? Kind of the same thing we've been doing all day. All right, let me try to wrap this up. Copy 25 minutes to 229. Product rule, right? Factoring, I think we got that. 25 minutes, 229.92 nanograms per milliliter. So it's a critical value. Okay. Okay. Second, so they use a second derivative, that's fine. They get a negative value when they plug 25 into the second derivative. So that means that the original function is concave down. So that means we're working with the maximum value. And so this is a graph of the original function, the concentration from the time it's administered and over time. What's the concentration in the bloodstream based on this data? And this is what it looks like. Now this is interesting. Like suppose you didn't have this function, but you could collect the data, right? You had this like drug or whatever, and you would administer it and you would start the timer, right? And then maybe you took the time like according to this, you can maybe check for the concentration maybe either every 10 minutes or every 5 minutes. And so like if you can collect that data and do it over, a couple of hours, every either 5 minutes or 10 minutes, you should get data that should kind of fit this. It wouldn't be exact. So then you would try to do like a regression line or something, like a best fit model. Then see, can you generate some kind of function that would fit the data, right? And then once that's probably how they kind of generate these functions, right? It's just interesting. Just like, okay, how are we doing this? But it makes sense. Like if you collected this data, then you could do a line of best fit. And then what kind of model are we using? Is it straight exponential, or is it, this one looks like it's the product of t and an exponential decay. So it's not directly, but they had a model already ready to go. It's really interesting. It's really interesting stuff. Maximum profit occurs at those values where the first derivative of revenue equals the first derivative of the cost function, and R double prime is less than C double prime. Okay. I'm going to have to leave this as an exercise because we're out of time. Yeah, this was a little bit kooky too. I think I did it in my video, but I know it tripped me up because it's just the structure of it is a little bit weird. But I'm going to have to rely on my video there. All right, gentlemen. Are there any burning questions before we go our separate ways? Let me make a copy of this available. Oh, that's not the right folder. Spring, traditional, calculus, notes, updated. Come on. Come on, thank you. Updated daily, right there. And we did do that one last time. Let me send it to the box. So when this bar finishes loading, you should be able to access a copy of anything that we were writing today pertaining to this section. And if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your evening. And we'll meet back on Wednesday for section 3.6 before we break for spring break. All right, gentlemen, take care. Peace. Let me check for you guys in Zoom real quick.
Have a good one.
Take care. All right, I'll give him credit. Even though he missed some. So like this. Everybody else is like this. All right. So there was something I needed to update as well. Let me go ahead and stop this.